All right, let's get right into it. If you're prepping for a machine learning interview, you're probably cramming algorithms. But what's the thing that really separates a good candidate from a great one? It's all about a deep, practical grasp of data pre-processing. In this explainer, we're going to break down the key concepts interviewers use to test if you're ready for the real world, from handling messy data to dodging that silent model killer data leakage. And this quote right here, this is the core philosophy. Look, anyone can import a fancy model from a library, but building something that actually works, that starts way before the modeling step. Interviewers want to know if you can take raw, messy, real-world data and craft features that give the model a fighting chance. This isn't just a nice saying, it's the bedrock of practical machine learning. So, here's our game plan. We'll kick things off with why this stuff is the real differentiator in an interview. Then, we'll dive deep into handling missing data and transforming your features. After that, we hit the big one, data leakage, before we run you through a quick interview gauntlet. And to wrap it all up, we'll give you a super practical checklist to make sure your work is always production ready. Okay, let's get into our first major topic, dealing with missing data. How you answer questions about this tells an interviewer so much about how you think. It's not about just memorizing some function name. It's about having a principled, almost like a doctor approach. Getting this right is a huge green flag for them. So just imagine it. The interviewer hands you a data set, and it is full of holes, just null values everywhere. And they ask you this exact question. What's your first move? If you immediately jump to, oh, I'd fill it with a mean, well, you've already skipped the most important part. And this is the answer they are looking for. A top candidate doesn't just start treating the symptoms. They diagnose the cause. You have to first investigate the reason, the mechanism behind why that data is missing in the first place. Your entire strategy for how to fix it depends on that diagnosis. And there are basically three main types. First, you've got MCAR, or missing completely at random. This is when the missing values are totally random, like a glitch in the system during data entry. Then there's MAR, missing at random, which is way more common. This is where the probability of a value being missing is related to another variable you do have. The classic example, older people might be less likely to report their income. The income is missing, but it's related to age, which you can see. And finally, the trickiest one, MNAR, or missing not at random. This is when the reason it's missing is related to the value itself, like people with super high incomes just choosing not to tell you. So here's where your diagnosis connects to the treatment. If you figure out the data is MCAR and there's only a few missing values, you know what? Just deleting the rows is probably fine. But if it's MAR, doing that will introduce bias into your data set. In that case, you got to get smarter. Maybe use something like KNN imputation that looks at similar data points to make an educated guess. Knowing these trade-offs is what they want to hear. Okay, so our data is now complete, no more missing values. The next step is getting our features ready for the model. This usually comes down to two big things, encoding our categorical variables and scaling our numerical ones. And the choices you make here, they can totally make or break your model's performance. For categorical data, you've got two main players, one-hot encoding and target encoding. One-hot is the safe, simple choice. It just makes a new column for every single category. The problem? If you have a feature with thousands of categories, your dataset just explodes. Target encoding, on the other hand, is powerful. It replaces the category name with the average of the target variable for that category. But, and this is a huge but, it's super risky and can easily lead to data leakage if you're not careful. More on that in a bit. Now, what about numbers? Do you always need to scale your numerical features? The answer is a definite no, and knowing when is a classic interview gotcha. Here's the deal. Any model that cares about distance, like k-nearest neighbors or SVMs, absolutely needs scaling. Same for models that use gradient descent, like neural networks. Otherwise, a feature that goes from 0 to a million will totally dominate a feature that goes from 0 to 1. But, and this is the key takeaway, tree-based models like Random Forest or XGBoost, they couldn't care less. They just split data at certain thresholds, so the actual scale of the numbers doesn't matter to them at all. Okay, this brings us to what is, without a doubt, the most important topic we're going to cover, data leakage. It's sneaky, it's destructive, and it's the #1 reason people build models that look fantastic on their computer but completely fall apart in the real world. Any hiring manager worth their salt is looking for candidates who deeply understand this. So what is it exactly? To put it simply, data leakage is when your model gets to cheat. It's exposed to information during training that it will never have access to when it's making a real prediction. Think of it like giving a student the answer key before a test. Sure, they'll ace it, get 100%, but did they actually learn anything? Nope, not a thing. And this little story is the perfect example. Let's say you're building a model to predict if someone will default on a loan. You create this awesome feature, days since account closure. The model trains, and wow, 99% accuracy. You're a genius, right? But hold on. When you're trying to predict a future default, how could you possibly know when the account will be closed in the future? You can't. That information is from the future. Your feature has leaked the answer, and your amazing model is completely worthless. So how do we stop this from ever happening? The industry standard, the professional way, is to use pipelines. You package up all of your pre-processing steps, your imputer, your scaler, your encoder, all together with your model into one object. Then you follow one simple, unbreakable rule. You split your data first, and then you fit the entire pipeline on the training data, and only the training data. The pipeline learns all the parameters it needs from the training set, and then it just applies those learned transformations to the test set. This isn't a suggestion, it's a non-negotiable discipline. All right, it's time for the interview gauntlet. I'm going to throw a couple of rapid-fire questions at you that hiring managers love to ask to probe your real-world practical knowledge on these exact topics. Let's see how you do. First question. You have a feature like user ID or zip code that has thousands, maybe even millions of unique values. One-hot encoding is obviously not going to work. What's your play? Okay, so a weak answer is to just say one-hot encoding anyway. A good answer is to suggest target encoding. But the expert answer, the one that gets you hired, is to suggest target encoding while immediately pointing out the risk of data leakage. And then you propose the solution, implementing the target encoding inside a cross-validation loop. This ensures that the encoding for each fold is calculated without ever peeking at that fold's answers. That shows you know the tool, you know its dangers, and you know how to use it safely. Next up, you've trained a linear regression model, but every time you retrain it on a slightly different chunk of your data, the feature coefficients go wild. They're totally unstable. What's the number one suspect, and how do you prove it? Your first thought should immediately be multicollinearity. It just means some of your predictor variables are highly correlated with each other, so they're redundant. The first thing you do is check a simple correlation matrix, but the real pro move, and what you should say in the interview, is to calculate the variance inflation factor, or VIF, for each feature. It literally tells you how much the variance of a coefficient is being inflated by other features. Any VIF score over 5 or 10 is a huge red flag. Phew. We have covered a ton of ground, from playing doctor with missing data all the way through the interview gauntlet. So now let's pull it all together into one simple, powerful checklist you can use to build rock-solid, leakage-free models every single time. This right here is your final takeaway. Number 1, split your data first, before you do anything else. Seriously. 2, get to know your data, profile it for missingness and outliers. 3, use pipelines. It's like putting guardrails on your process. 4, fit those pipelines on your training data only. 5, apply the exact same learned transformation to your test data. And 6, use cross-validation with your pipeline to get an honest estimate of how it'll do in the wild. If you follow these steps, you are building models the right way. And at the end of the day, this is the question you always need to be asking yourself. Because a model that gets 99% accuracy is completely worthless if it just cheated to get there. The whole point of this is to build models that actually learn the underlying signal so they can generalize to new, unseen data. Master that principle, and you're going to nail any ML interview they throw at you.